And today I'm going to explain about the Charlie flexing, the coding and the demonstration. So for here, first you start off with including derivative.h, and second we'll start defining the input mask right here. We define input 1 as 1 shift to left 1 time, and input 2 1 shift to left 0 times, and input 3 1 shift to left 5 times, and the same goes for output 1, 2 and 3. And then next we will start the function prototyping right here. Alright, and after that the definition for initialize Charlie plexing function will be as follow. First off, we'll start off with enabling the clock to all of the port that we are using. Second, we are setting port E PCR 0, which is E0 equals to port PCR max 1. Max 1 stands for digital input or output, and then or port PCR underscore PE mask, which is stand for pull enable, and port enable port PCR PS mask, which stands for active high, Alright, same goes for port E PCR 1 and port A PCR 5. So for the output, we will set port D PCR 4 equals to port PCR max 1, which stands for digital input output, port PCR DSE, which stands for high drive strength, and then PCR PE mask, which stands for pull enable, and PCR PS mask stands for active high. And the same go for port C PCR 8, port A PCR 1. And moving on, we'll set the data direction input for port E. As you can see here, it's N equals to not input 1 and input 2, which means setting port E as an input. Same thing, same case go for A, GPIO A as well, PDDR, and equals to not input 3. Alright, moving on, we'll move to void set LED, right, the function. So if the void set LED get a 0 value, we will set GPIO D, GPIO C, GPIO A as an input to produce a high impedance state, which eventually turn off all the LED. And if it returns 1, then GPIO D and C will be the output, which will give out a high, and GPIO A PDDR and equals to not output 3, which will turn the GPIO A into an input, which will produce a high impedance. And for the D and C, we will for D we will set it we'll make it a high, and for GPIO C we will set it a low. So same case for LED num 2, 3 code, and 4, 5 and 6. Right, moving on, we will move to INT read input. First we start off with the initialization and defining E1 is equals to GPIO D underscore PDIR and input 1. This is used to tell that E to take the value of all the values from port E and input 1. So this will be our first input, and E0 will be our second input, and A will be our last input, which will be input 3. Now here I bit pull it 5 times, and E1 I bit pull it 1 time, so I can check if the value is a 1 or a 0. So if all the ports are 0, I will return 0. And the same case go for this. If conditions, I return a 1, and this I return a 2, or this condition I return a 3, 4, 5, 6. But if all the ports receive a 1, I'll return a 0. Means that if all the ports are high, I'll turn off all the LEDs. Now moving on to the last part, which is the main. First we start off by initializing the counter, and we initialize the Charlie-plexing, which is initializing all the ports. And then infinite loop, for infinite loop here, counter will be equals to the read input, which will get the data from the read input function. After we got the value for the counter, we will set the LED. Now I will debug the code here. Alright, a few seconds. Okay, and I will start the code program. So moving on to this demonstration right here, as you can see, all the LEDs are turned off because all of the switch are off. So if I turn the first one on, the first LED will light up, and if I set it as a 10, the second LED will light up. If I set it to 1011, third LED. Now if we set it to 100, fourth LED, 101, fifth, 110 for the sixth LED. If all are high, LED will turn off. That's all for this part. Thank you. Today I'm going to explain how to convert the signal, the analog signal from potentiometer to digital signal and display it on Kitty. First, we'll include the headers, which is clock.h, derivative.h, and serial.h, and function prototype, these three functions. Before we jump into the main, let's go take a look at the do ADC conversion, and I initialize ADC and delay function. First we'll declare some just some random variables to help us to display the decimal points for the signal from the potentiometer to digital and displayed on Quincy. And this is the calculations, alright, and after that we put some delay there to show the result, to display the result. And second, we'll move to initialize ADC. This one setting them as 0 to make it, to set everything as 0 to make sure that it's 0, to make sure it's not some random values. And this one we make it 0 or CFG mode 0 hexa 02. And as you can see here, we've closed the diff because we use an not ADC SC1 diff mask. And next is just this delay function, which is some delay function. And for the main function, first we clock initialize first, and then we trigger the clock for analog for the analog port. That's why we are using SCGC6. After that, we'll initialize ADC. For infinite loop, do ADC conversion. This will be the function that will constantly print out the value from the potentiometer to Kitty. Now let's do some demonstration with this. Before that, I'll run this program first, and I'll run Kitty as well. Okay, running and run. Okay, as you can see, Kitty is printing out the voltage 3.0 with 2 decimal place. Now I'll change the resistance of the potentiometer. See, as I'm spinning, as I'm changing, the voltage is dropping. Okay, and it's dropping. And if I turn more, eventually the voltage will become 0 volt. And it's in 2 decimal places. Thank you.
I'll be explaining the modify part 2, which is supposed to be the modification of the circuit of the potentiometer. So the first thing we did here was we initialized, we wrote down the headers, we included the headers, derivative detach, STO detach, and cloud detach. In addition to that, we included the project header files that we were given. We added several ones, and in addition to the source files, we added 2 more. So next we prototyped the certain functions that we used. The main one for the part 2 is the initialize ADC, calibration of ADC, the conversion function, and the delay function. The others are not important for now. The first function I'll be talking about is the calibration function. This function is not really necessary. We just added it because we want to confirm that the ports are working, but really you don't need it. So what we did, we just set some values for the configurations and the status and control registries. So we just set some values there, and then we tested if the calibration is successful or not, and we returned the values. I'm sorry, not return, we just display. The next function is the initialize function. This function we were calibrating, and then we're waiting for some time. Then we just set some initial values for CFG1, configuration 1 and 2, status and control 2, status and control 3, SC1A. So we're setting them all to 0 for the CFG1, except for the mode we want it to be, we want to use 10 bits. For the SC1A, we shut down the DIFF. The next function is the conversion function, which is probably the most important one beside the initialization. In this function, we declare the variable called result, and then we set everything in SC1A as 0, except for the inputs. We used channel 19, which is the one connecting to the light sensor, and then we while looped while there is while the conversion is not complete. We do nothing. Once it completes, you just store the results into the variable called result, yeah? And then you return the results. And then the next one is a delay function. You don't really, it just to give some time to read the values from Kitty. Inside the main function, we called in a clock initialization, which is a predefined function in the clock detach, and then we calibrated, we initialized, and inside the while loop we stored the conversion function into a light level. We printed that light level, and then we okay, that's it, and then we delay it, and then we keep on doing that. So I'll now show you the readings of the light sensor. I open Kitty. Let me build it first. I'll build it first. Okay, wait for it to build. So we open in Kitty. Okay, as you can see, it prints out the light value. It's a constant, almost a constant, because there's no light change. And then I'll use a flashlight to change the value. So as I'm flashing with the light sensor, you can see that the light value is getting smaller. This is me flashing, and this is removing the flashlight. I'm flashing it again. As you can see, it varies greatly, and the brighter the light goes, the smaller the value. So this is very bright, and that's very dim. Okay, so that's it for the first part. Now the next one here, the next one we're doing here is the Charlie plexing and ADC, which is part 3, the application integration. In this part, we want to combine the ADC and the Charlie plexing. So what we did, we combined the previous functions, which Chester explained in the first video. which is the initialized Charlie plexing and the set LED. We removed the function of the read input because we didn't need to read an input. We just need to compare the values of the from the light sensor and then set the LEDs. So the only difference here is removing the read input and changing the set LED conditions. So the set LED conditions is quite the same. We just changed how we read what are the readings. So in this case, this is our first condition. If it's too dim, we shut down all the lights. We shut down all the LEDs. And then this is lighting the first, second, third, fourth, fifth, and sixth LED. So I'll test it now. In the initialize function, we also remove the inputs because we no longer need them. So the main function here, inside the main function, we read the LED value we display on kitty, and then we set the LED as the readings, and then we set the LEDs again. I'll run the program now. I'll debug it to test it. It's already running now, so you can just straight away show it. So this is the first state. This is the second state for the first LED, third, fourth, fifth, last states. Second, third, fourth, fifth, sixth. Okay, that's it. That's it for the Charlie plexing LED.